Hello, my name is Madina. I'm a data scientist at the Institute of Smart Systems and Artificial Intelligence. Today we're going to review another chapter in computer science basics. The purpose of this video is to give the intuition behind the major notions of time complexity. Before we begin, please keep in mind that there are many ways to solve problems. Some are more efficient than others. With small amounts of data, the difference is negligible. But as the size of the data grows, the issue of efficiency becomes much more important. We will see how the right choice in the design of an algorithm can make a huge difference between a problem that can be solved in a reasonable amount of time and the one that perhaps cannot. Let's begin with the simple task of finding a word in a sentence. Here we have the first sentence of the first novel in the Harry Potter series. Mr. and Mrs. Dursley of number 4 Privet Drive were proud to say that they were perfectly normal, thank you very much. To prepare the data for our task, we go through three preprocessing steps. First, remove punctuation as it is not relevant for the search. Second, treat the upper and lowercase letters the same to resolve any confusion. And third, sort the words in alphabetical order. As the result, we get the following sequence of 22 words. Suppose we are looking for they, which is the 17th word in the sequence. Let's start with the simplest approach, where we go through every element from left to right and compare it with our target word. This is called linear or sequential search. Note that every step takes only one comparison, so we finish the task in 17 steps. Let's go through a few iterations of linear search. At the beginning, we check if the first word and matches our target they. It does not, so we go to the second element in the sequence. As you can see, the same happens for the next 15 steps until we reach the 17th word, that is indeed they. Now we're going to look at binary search, another method to perform the same task. With binary search, it will take only 5 steps instead of 17 to find our target. The secret ingredient is the alphabetized data. Before we dive deeper, let's cover the basics of binary search. At every step, we keep track of our search space using three index values: low, the starting point; high, the ending point; and mid, the middle point between these two indices. At the initial stage, we set low to 1 and high to the size of the input, which is 22 in our case. Now we go to step 1. At this point, our search space includes the whole sequence. We compute mid using the formula and set it to 11, which corresponds to perfectly. Alphabetically, perfectly is lower than they, and since the sequence is sorted, we know that everything to the left is lower than perfectly, which means that in our search for they, we can ignore the whole left half of the sequence and continue with the other half. We do so by updating low to 12 while keeping high the same. As the result, we look at the right of perfectly and move to the next step. At step 2, the search space is shrunk by half. Mid is updated to 18 and points to 2, which is alphabetically higher than they. So we look into the left half of the current search space and update high to 17. Steps 3 and 4 go in the same fashion. At step 5, we're left with a single element in the search space. Low, mid, and high point to the same word in the sequence, which corresponds to the target they. Our work is done. Using the same example, we will explore the ideas behind the best and worst case scenarios. In the best case, we have the minimum possible number of steps. For linear search, it would be only one step, where the target is the very first word in the sequence. For binary search, it also takes only one step, but their target should be located in the middle. In contrast, the worst case scenario takes the worst possible or the maximum number of steps. For linear search, it is the size of the sequence, as we have to walk through every single element. The target word would be in the very end, 22nd in this case. For binary search, counting the maximum number of steps is not as trivial. To explain why, let's visualize the trace of the algorithm with a binary tree. This is a binary tree because every node has at most two children, Every node in the tree contains a mid-value. Every level of the tree corresponds to the step in the algorithm. For example, the root node contains 11 because at level 1, meaning at step 1, the mid was calculated to be 11. Remember that depending on the target, we would either go to the left or right side of the data. This is why every node has at most two children, corresponding to these decisions. For example, the right child of 11 is 18, which is the midpoint we calculated earlier for the right half of the sequence. The left child is 5, which is the midpoint we could have calculated if we went the other way to the left portion of the sequence. Remember that at the first step of binary search, the size of the search space equals to the size of the input data, which is 22 in this example. As we go further down the tree, we keep cutting the search space by half, and we continue doing so until we reach a single element. So the total number of steps the algorithm requires is the height of this tree, which is 5 in this example. Located at the last level of the tree are the leaf nodes that represent the worst case scenarios, meaning for, much, of, proud, thank, they, and you would all require 5 steps to be found, and this is true for a 22-word sequence. Now we will generalize this calculation to any input size. Suppose instead of 22, we're given a sequence of size n. At any level with index L, the size of the remaining search space can be expressed as n divided by 2 to the power of L minus 1. For example, by the time we get to the level 3, the original search space was cut by half 2 times. So the size of the remaining search space is n divided by 4, which is equivalent to n divided by 2 to the power of 3 minus 1. As we know, the search space at the last level consists of a single element. So if L is the index of the final level, then we can set the equation to 1 and express L as log base 2 of n plus 1. So in the worst case, the algorithm takes log base 2 of n plus 1 steps. To verify, let's set n to 22, and we see that the maximum number of steps is indeed 5. To sum up, if n is the input size, then the maximum number of steps for binary search is log base 2 of n plus 1, while for linear search, it is simply n. Now, instead of a single sentence, let's do search in the whole novel. With nearly 77,000 words in total, performance difference is pretty dramatic. In worst case, around 77,000 steps for linear search and only 17 steps for binary search. As we increase the word count with every book in Harry Potter series, the advantage of binary search becomes even more evident. As the size of the data increases, the growth rate for the number of steps is much slower. It goes from 17 to 22, while linear search jumps to over 2.5 million steps when all books are combined. To sum up, with the help of Harry Potter, we just analyzed how many steps a search would take in terms of word count, and then we observed the growth rate as the count increased. Keeping this in mind, let's go back to time complexity. The fundamental question we're dealing here is how much time does a program take? Estimating the exact runtime in seconds or minutes is hard, as it depends on the program implementation and the machine where the program runs. Instead, we use a combination of the two ideas that we just covered. First, estimate runtime in terms of input size, and second, analyze the growth rate as the input size increases. We formally express the growth rate using a big O notation, which consists of different complexity classes to define the upper bound for runtime. Linear search belongs to the linear complexity class, where the runtime is proportional to the input size. Binary search is an example of logarithmic runtime. Here is a graph from bigocheatsheet.com that puts together the most common complexity classes. Besides the familiar logarithmic and linear running time, we got constant, log linear, quadratic, exponential, and factorial. We previously discussed how linear time is inferior to logarithmic, but this graph presents even worse types of orders of growth. Take a look at the red zone. The rapid growth in the number of operations is staggering there. In practice, it is common to work with large amounts of data, so we have to be careful with the design of our algorithm. If we choose a solution with a fast asymptotic growth rate, then it can blow up pretty hard. To illustrate this issue, let's revisit the task of searching for a word in the Harry Potter series. Suppose we have additional solutions that belong to log linear and quadratic complexity classes. One can argue that current machines are powerful enough to handle linear search with 2.5 million operations in a reasonable amount of time. But it might not be the case for nearly 6.7 billion operations resulting from a quadratic growth rate. In summary, as the size of process data increases, the time it takes to perform a task can increase at a different rate. The slower it grows, the better, which is critical when operating with large-scale datasets. If you like this video, please consider subscribing to our channel. Comments are welcome, and check out other videos on our eSci channel.